Welcome, everyone. Welcome. Just waiting a minute for people to join. Welcome. We will get started in one moment. Well, greetings and welcome, everyone. My name is David Sandelow. I am the inaugural fellow at the Center on Global Energy Policy at Columbia University, also the chair of the ICEF Innovation Roadmap Project. Our topic today is carbon mineralization and how carbon mineralization can help fight climate change. That is the topic of this year's ICEF Innovation Roadmap. This event is being webcast live. It is on the record, and a recording will be available on the website of the Center on Global Energy Policy in several days. For those of you joining us by Zoom, you can submit a question in the Q&A, and we will be taking questions after we make a presentation on our roadmap. Really delighted to be joined today by three of the co-authors of this roadmap, three extraordinarily distinguished experts in their fields. In alphabetical order, Dr. Julio Friedman, who is a senior research scholar at the Center on Global Energy Policy here at Columbia. Dr. Peter Kellerman, who is the Arthur Stork Professor in the Department of Earth and Environmental Sciences at Columbia University, and Sasha Wilson, who's a professor in the Faculty of Science, Earth and Atmospheric Sciences at the University of Alberta. Welcome to everyone. And with no further ado, we will get started with our presentation, which I will share. Hope everyone can see this. Is that good? If it isn't, somebody please let me know. Great. So this report on carbon mineralization was produced by a team of co-authors, several of whom are with us today, released last month. This is part of a series of roadmaps that has been done in recent years as part of the ICEF conference, which is held in Tokyo every year. Our topic this year is carbon mineralization. And I have found that many people who work on climate policy are not familiar with this topic. And so just to start with some basic introductions, what is carbon mineralization? It's a process in which carbon dioxide becomes bound in rocks as a solid mineral. It happens naturally as certain rocks are exposed to carbon dioxide. And in this natural process permanently removes about 0.3 gigatons, 300 megatons of carbon dioxide from the atmosphere each year. That is roughly 1% of all the energy emissions in the world each year, about 0.6% of total greenhouse gas emissions in the world each year. And our kind of top line conclusion, to sum it up quickly, is that carbon mineralization can help fight climate change. And three key points here. First, it is the most permanent form of CO2 removal and sequestration available. It binds carbon dioxide into solid rock. Second, very importantly, the chemical reactions that mineralize carbon dioxide do not require energy inputs. A key feature, very helpful, these processes they actually release energy, they're exothermic. And then third, the mineralization resource that makes this possible is effectively unlimited and located in dozens of countries around the world. And with that, let me turn this over to Professor Peter Kellerman, my friend and colleague at Columbia University.
Hello, everyone. Sorry, I'm just adjusting my camera here. So thank you very much, David. There are two broad approaches to carbon mineralization. One is to bring the CO2 to the rock, so to speak, by injecting carbon dioxide-rich fluids, either CO2-rich water or supercritical CO2 fluids into rock formations deep underground. That's also known as in situ mineralization. Or alternatively, one can expose crushed rocks on the Earth's surface to CO2-bearing gases, either air or gas enriched in CO2, which is known as ex situ or surficial mineralization. Next slide, please. Whoops. Carbon mineralization can satisfy several needs. It can be used to remove carbon dioxide from the air directly while producing pure CO2 for permanent storage or use elsewhere. That's a surficial process. It can remove CO2 from the air and combine it with permanent storage in solid minerals. That can be done on the surface or beneath the surface or underground. And finally, it can permanently store CO2 that's previously captured elsewhere in solid minerals, and that too can be done on the surface or underground. Next slide, please. Whoops. As David mentioned, this is the carbon mineralization process is a natural one. Oftentimes rocks from the Earth's interior erupt or are emplaced by plate tectonics near the surface, and they're far from equilibrium with the atmosphere and surface waters. So they react with CO2 in the air and groundwater to form carbonate minerals, and also they transport dissolved carbon into the ocean. Next slide, please. Here's a map of the carbon mineralization resources worldwide, with the size of the circles corresponding to the size of the reservoir, and the color of the circles corresponding to rocks that are relatively rich in magnesium and calcium, basaltic lavas, and rocks that are extremely rich in magnesium, periddotites and serpentinites. So you probably don't have time to take all this on board in the course of a presentation like this, so I'll just tell you that the resource for storage of CO2 via carbon mineralization exceeds 100 trillion tons, and so many thousands of years of human emissions at present day rates. Next slide, please. Okay, I don't want to go through this complex slide in detail, but when we turn to underground methods, we can distinguish between storage methods, where we take gas or fluid that's already been purified by some kind of carbon capture method, perhaps associated with a power plant or a concrete factory, and take that CO2-rich material underground where it forms solid carbonates for permanent storage. On the right side, we can think about carbon dioxide removal from air directly. We can take surface waters that are saturated in CO2 and air, circulate them through the rocks, removing almost all the dissolved carbon, and then we can return those fluids now depleted in carbon to the surface, where they will draw down carbon dioxide from air. We can also envision hybrid methods where we use machines for direct air capture of CO2 to produce gas that's enriched in CO2, but maybe not 100% CO2, and then react those fluids with rocks. Next slide, please. On the surface, we can call this enhanced rock weathering. We can use crushed rock to remove carbon dioxide from air, either near a mine site producing magnesium-rich materials, or dispersed as rock powder over large areas, for example, as we add lime to agricultural soils routinely. The crushed rock material can permanently store billions of tons of CO2 per year on a full life cycle basis, both as solid carbonate minerals in the soil and as dissolved CO2 in the groundwater, which is enhanced by the presence of dissolved rock material, calcium and magnesium. The carbonated rocks can also be heated, so we could have a tray, let's say, of calcium or magnesium rich material, that takes up CO2 during weathering, and then that can be heated to produce pure streams of CO2 for sequestration elsewhere, and then distribute the calcium and magnesium again over large areas to remove more carbon dioxide from the air in a looping process. Next slide, please. The main advantages of these methods are that it's very simple. You could probably do it with existing agricultural machinery. It's consistent with current mining and agricultural practices. And in some cases, adding calcium or even magnesium to soil can improve soil productivity and agricultural production. The main challenges are there could be environmental risks from accumulation of metals, including nickel and chromium in agricultural soils. And very challenging in some cases is a lack of widely accepted measurement methodologies for measuring small changes, for example, in the carbon content of soils over huge areas. Next slide, please. So examples of crush rock goals and methods would again be carbon dioxide removal from air via looping. So one could, for example, heat limestone, calcium carbonate, to produce calcium oxide and CO2. You take that CO2 and permanently store it or use it elsewhere. And then you take the calcium oxide evolved from heating and expose it to the air again to form limestone again in a few days to weeks. Then repeat that process over and over again, using the calcium to capture many, many times its mass in CO2. One can also use achieve carbon dioxide removal from air with storage via distribution of crushed rock material in agricultural soils. This is a one-time use, but it might be extremely inexpensive and result in long-term storage of CO2 from air. Finally, one can use crushed rocks to store CO2 where we have CO2 captured elsewhere, captured and purified elsewhere, and expose it to calcium or magnesium-rich silicate rocks to form solid carbonate minerals for permanent storage. Next slide, please. I think at this point, I'm going to turn this over to Professor Sasha Wilson at the University of Alberta.
Thank you very much, Peter. On the last slide, Peter introduced us to this idea of using crushed rock resources for carbon mineralization. And one question we need to ask is, how are we going to source all of that material? And it turns out that we already produce vast amounts of finely pulverized calcium and magnesium-rich wastes that are ideal for storing CO2 in a mineral form. And these wastes come from mining and industrial processes. So these resources that we already produce could provide hundreds of millions of tons of CO2 removal and sequestration per year across many dozens of countries. And the key industries that produce wastes that are ideal for this process include iron and steel making, coal power generation, which generates reactive fly ash that can be used to bind CO2 in a mineral. And these also come from fertilizer production, as well as the mining industry, which produces about 500 million tons of highly reactive to CO2 materials every year. In addition to annual production of these calcium and magnesium-rich materials that can be used to bind carbon, we have feedstocks of many billions of tons of mining and industrial wastes that have been piled up since the start of the Industrial Revolution. And these are available as a feedstock to kickstart carbon mineralization. In some cases, mineralizing these wastes also has very valuable co-benefits. For instance, it could significantly reduce the cost and environmental impact of disposing of these wastes, which are currently just stored and stockpiled today. So there's a very attractive pathway to utilizing these materials and removing and storing CO2 within them. The largest potential for industrial waste as a mineralization feedstock comes from China, with its large coal power generation system and iron and steel making, as well as active mining industry. And that would be followed by India. But again, these resources and industries are present in many dozens of countries around the world. Next slide, please. And so here's a view of a few alkaline industrial waste piles, so you can start to appreciate the scale of them. And the one on the left is actually quite small for an industrial waste pile. This is a pile of calcium-rich phosphogypsum waste. And so this is produced as a byproduct of fertilizer manufacture. And so waste like this, only a small fraction of them are being utilized today. So this is a valuable resource that we can employ. And so these waste piles can help remove CO2 from the atmosphere. They can also be used as a resource to store CO2 that's been purified and refined from other sources. And the greatest co-benefit here is that we can eliminate these waste stockpiles and use carbon mineralization as a pathway for remediation of these wastes, while also creating jobs, for instance, increasing the longevity of mining operations by turning them into operations that mine carbon from air. Next slide, please. The other industry that creates a huge amount of material that is readily used for carbon mineralization is the cement and concrete industry. Cement is a very calcium-rich material that's generated by heating up calcium carbonate rock, limestone, and burning off the carbon dioxide. And so cement is that key component that goes into making concrete. And because we're taking a natural rock that's already bound carbon dioxide within it and burning that CO2 off to make concrete, cement and concrete are responsible for approximately 8% of global CO2 emissions annually. Now, this material has a very high potential to win back that CO2 through carbonation. So we could take that material, react it with CO2, and store it once again, just as it was in the original rock that was used to manufacture concrete. Unfortunately, there's a low potential for CO2 removal, but by reacting cement and concrete with CO2, mineralization in combination with other strategies could lead to a fully carbon neutral or even carbon negative concrete industry. Next slide, please. And at this point, I'd like to turn over the slides to Dr. Julio Friedman.
Thank you much. Thank you so much, Sasha and Peter and David. And thank you everyone who's listening. Let's show what we discovered. First finding is on the potential. Part of the reason we're so excited about this is that the potential is enormous. Specifically, the potential to remove and permanently store many gigatons of CO2 in the area, in the atmosphere, looks like it's on the order of 10 billion tons a year. That's just a lot. That's twice the size of the oil and gas industry. This reference does not include a time frame, but the volumes, the potential, the fluxes are very much in this order. We estimate that if we had strong policy support, they could take these technologies and approaches that Dr. Kellerman and Dr. Wilson mentioned, then we could scale to, say, a 1 gigaton by 2035 and multiple gigatons by 2050. Next slide, please. Why should you care? Why do you like this? The primary reason why is that the strategy for removal and reduction and sequestration has a lot of strengths, has a lot of merits. Specifically, it is, as David said, at the top, the most permanent form of CO2 sequestration. The risk of return is extraordinarily low. Second, you don't need energy inputs. So these are exothermic. Per one of the questions, these are slow reactions. These are kinetically limited, but they are not thermodynamically limited, which makes this a plus. Third point is that we basically have an unlimited resource and it's broadly distributed around the world. Last point is that the costs appear reasonable and there's clear lines of sight to reducing those costs. Next slide. Third set of findings is there's issues, unsurprisingly. First one is that point I'd mentioned earlier. The kinetics are slow. So if you want to overcome the kinetics, you have to do things like additional grinding, stirring, injection. There's some set of actions that you need to do, adding heat, adding acids. So you have to take additional actions to make this useful. Second, the distribution is broad, but it's only coarsely understood. People do not generally go out and explore for brucite. So we don't have the clearest understanding of where the extra good stuff is and how quickly it would take to come online. There's some assessment work to be done. Third point is literally you're making rocks. Rocks do not sell for lots of money. Aggregate is on the order of $10 a ton. So you're not going to probably become, carbon Jim Brady by selling rocks. So we need to think about ways to pay for the work that are not just selling the product. Last but not least, policy framework recognition today is effectively zero. This is not a compliance mechanism within the ETS. It's not a compliance mechanism within the low carbon fuel standard in California. It is a sufficiently new idea that policy frameworks today do not understand or include carbon mineralization in their work. Next slide. This is an important finding. Despite those challenges, there's stuff we can do. And if there's one and only one thing to do, it's pilots. Go out there, grind some rocks, find some carbon, learn stuff. A handful of pilots in a handful of geographies could profoundly reduce the uncertainty regarding the viability of this. How efficient is it? How effective? What's the costs? And it would allow us to develop better standards and protocols to monitor and validate the CO2 removal. A handful of pilots gives you a lot of answers. Next. Finding 5, there is a distinction between removal and storage. As Dr. Kellerman pointed out, carbon mineralization is not one thing, it's many things. And some of those things capture CO2. In that process, sometimes they also remove it, but sometimes they don't necessarily. So exampling is you can just weather rocks in a looping process, and that becomes a capture mechanism. It's another form of, say, direct air capture or point source capture. However, if you inject CO2 deep into the earth, that will permanently bind it. And there's several pathways we've talked about that both remove and permanently bind the rock. And so understanding that this is not one thing, there's lots of things and they can play many different roles, helps you differentiate whether the mineralization is doing removal and storage or doing removal or storage. Next slide, please. One of the things we wanted to do is compare this with something that a lot of other people think about. We did a direct comparison with direct air capture and tried to say how they're similar and what ways they might be different. So both of these are fairly early stage, and today both of these are pretty expensive. That shouldn't be a surprise to anyone who's been working in this space. It is also the case that both of these approaches have clear lines of sight to substantial cost reduction. Within the next decade, we could have 60 to 90% cost reduction in both. They can be deployed in many places around the world. And that's good because a well-mixed atmosphere has CO2 in it everywhere in the world. And both approaches show considerable promise. They both have large capacities. They both have straightforward scalability. And so they are viable components to a net zero solution. Direct air capture and carbon mineralization are distinct in important ways. One important way is that carbon mineralization requires far less energy to do the job. So in an energy constrained world over the next 20 or 30 years, we may choose to use energy in many different ways, including direct air capture. But because this requires minimal energy inputs, it is in some ways more actionable. Second, there are straightforward co-benefits. For example, enhanced soil fertility, feedstocks for building materials. You are, in fact, doing stuff and making stuff in a way that provides some additional value. Some of the approaches we've talked about are more difficult to measure and monitor for mineralization. Direct air capture has the benefit that it is straightforward to validate and monitor. Some carbon mineralization projects are also that good, but others are a little trickier, which is why there should be a science program that is paired with the field program and an innovation agenda. Last, I'm going to turn the floor back to my friend and colleague, David Sandalo, to give the final recommendations.
Thanks, Julio. So we make 4 recommendations in this roadmap. And the first is that governments and companies should invest in research and development on carbon mineralization, immediately launching dozens of new pilot projects in different places around the world, as Julio was just saying. Our second recommendation is that policymakers should add carbon mineralization to the portfolio of climate change mitigation options. We have found that there's almost no attention to carbon mineralization in the policy dialogue on climate change around the world. Of the more than 180 nationally determined contributions that were submitted to the UN Framework Convention on Climate Change, only one mentions carbon mineralization. That is the submission from Iceland, by the way. So among the policies that we recommend policymakers look at are incentives, including, very importantly, recognizing carbon mineralization as a potential compliance option in emissions trading programs. Adopting procurement preferences for carbon mineralization products, including cement, would be a big step forward. Governments around the world buy lots of cement. Streamlining regulatory processes while protecting public health and safety is also important. And then we recommend launching an initiative under the Clean Energy Ministerial and potentially other international fora to share learning and gain better understanding globally on this topic. Our third recommendation and fourth recommendation both have to do with the private sector. And our third recommendation is that mining companies and manufacturers should seek opportunities for carbon mineralization in their exploration and production activities. This is a great opportunity for mining companies and some manufacturers to achieve or help achieve net zero emissions in their operations. Mining companies and some manufacturers have significant alkaline waste, as Sasha was saying, and can really use those to great benefit. And then finally, any company in any sector with a net zero commitment should consider carbon mineralization as part of its portfolio of climate change options. The first and highest priority for any company is to reduce their own emissions to the maximum extent possible. But then when there are residual emissions, offsets using carbon mineralization are very attractive, in part because of the permanence of carbon mineralization projects. Our roadmap contains roadmap figures looking at specific recommendations in the near term, medium term, and long term. I won't go into details here, but if you're interested, please get our roadmap, which is available on the website of ICEF, which is www.icef-forum.org. We'll put the link in the chat. And our roadmap, we have 3 sections, one on policy and standards, one on fundamental and applied RD&D, and a third on corporate leadership. And we spent some time among our co-author group kind of talking through what we think could be done in the near term, in the medium term, and the long term. And so in conclusion, just to wrap it all up, kind of 4 key points. First, carbon mineralization is a process in which carbon dioxide becomes bound in rocks as a solid mineral. Second, carbon mineralization can remove many gigatons of carbon dioxide from the atmosphere each year. The next step is launching dozens of pilot projects worldwide, and policy and corporate leadership are essential. And so with that, let me invite my co-authors back on the screen and remind everyone I'm joined here by Julio Friedman of Columbia University, Peter Kellerman of Columbia University, Sasha Wilson of the University of Alberta. We are all co-authors, along with several other colleagues, of a new report on the topic of carbon mineralization and how it can fight climate change.
David, if I may interrupt briefly, I posted the link in the chat function, as well as the link to all the ICEF reports. That's
wonderful. Thank you so much. And I want to recognize our other co-authors who really played an important role in this. Dr. Colin McCormick Ian Power and Brianna Schmidt, all of whom are experts in this topic as well. We have a number of questions in the chat. Let me remind you also that if you've got questions, please send them to our Q&A, and we're reviewing them. Let me just start by asking Peter Kellerman to elaborate on some of his work on this topic, because it's so interesting. Peter, I know you've got a project off the coast of Oman, or in Oman rather, that I think the audience might be interested in. Just elaborate on what that project is and what you think the potential for it is.
Sure. So there is a startup called 4401. You can find them at 4401.earth, who are Omanis who are interested in commercializing some of the techniques for carbon dioxide storage underground. And they're taking advantage of the fact that Oman and the adjacent United Arab Emirates have the largest outcrop of magnesium-rich rocks from the Earth's interior of any place on Earth. Moreover, because some of the methods that we might use for CO2 storage subsurface involve a lot of water, it's important to mention that these rock resources are on the seacoast, so there's readily available, essentially infinite amounts of water available. So in a nutshell, that's it. And again, 4401.earth if you're curious.
Do you think are there many other places around the Earth where a similar type of process could be done, Peter?
Yeah, there's many places. So let's first focus on what's already happening. So there are magnesium and calcium rich lavas known as basalts, which are very widely distributed around the world. And in Iceland, there's ongoing storage of CO2 via carbon mineralization in those rocks. Again, if you want to look that up, carbfix, all one word, .com. And then the number of basaltic lava outcrops at and near the seacoast is very, very large and all over the world. Turning to the more magnesium-rich rocks that have a higher storage capacity for CO2, there's places on the planet, and of course you don't have to do this everywhere, especially if you're removing CO2 from air. You can just do it in the places that are optimal. So in that context, there are several places in the Western Pacific, New Caledonia, Papua New Guinea, and on a smaller scale, Japan, where the appropriate rocks are right on the seacoast.
Great. And Sash, let me turn to you and just to have you elaborate on the potential for what you were discussing, particularly in North America, because we have a global audience here, but I think it's slightly, typically for our events, a little over half of our participants are from North America, US and Canada. So
David, let me mention something. There's a huge amount of basalt on the coast in Hawaii.
Oh, okay, great.
Speaking of the United States.
Yep, road trip.
All right, sorry.
Sasha, just elaborate. Yeah, you mentioned China and India have particular potential with mining and industrial waste. How about in the United States and Canada?
Absolutely. Going back to that map that Peter was describing of where the best rocks for carbon mineralization are located. Here in North America, we're very lucky that we have great resources of calcium and magnesium rich rocks, so basalts, and also highly magnesium rich rocks, which are ultramafic rocks. And those rocks host most of our nickel, cobalt, platinum group element, chromium resources, as well as diamonds. And so in North America, there's we do have large stockpiles of these mineral wastes that have built up over the last few centuries, and we're generating more of them all the time. So there's a lot of opportunity there. And we do have a lot of expertise in mining as well. So many of the largest global mining companies have a large presence here on our continent. And so we have the expertise to implement these strategies, whether it's removal or storage or a combination of them in that sector. And also including steel and fertilizer manufacturing, those are other industries that are producing resources that we can use here at home.
Peter, you're raising your hand.
Yeah, it's worth mentioning that because of the perhaps exponentially growing demand for lithium, cobalt, nickel batteries, particularly in electronic vehicles. There's kind of a global nickel and cobalt rush going on right now, and there are quite a few large deposits of nickel and cobalt in this context that have not yet been developed, but are certainly being very, very actively considered right now in both the United States and Canada.
Thanks for mentioning that. And just to build on that quickly, our mineral processing techniques keep becoming more and more efficient as the grades of resources we're exploring for keep going down. So in a lot of these wastes, there's an opportunity to reprocess them for both carbon mineralization and extraction of critical resources that we need to build green infrastructure.
So just to elaborate on that for a moment, it's a really interesting point, because there is so much attention, at least in some of the material I read about the need for critical minerals in the new clean energy economy. Do you think that mining processes then can help contribute additional reductions as a result of this, or are we just talking about minimizing the total emissions from the mining processes? That is, could we do even better, than beyond zero by capturing some of the mineral carbon dioxide as a result of these processes? Any idea?
I think some of the, I'll just put some ideas out there first and turn it over to Peter. So some of the most promising work I've seen has been coming out of hydrometallurgy laboratories at universities, where they're looking at using carbon mineralization as a metallurgical tool. So what they're doing is they're carbonating the rocks during processing to extract nickel. And some folks are finding that this actually improves both the amount of carbon that can be sequestered in the rock, as well as the amount of the critical metals that can be extracted. So I think there's potential to turn carbon mineralization into an ore processing technology. And that's something I'm really excited about.
If I can just add briefly to that, we all have the sense that the answer should be hell yes. But this gets back to the need to do better assessments. This gets back to the need to do a couple of pilots. If you wanted to, really defend an investment in this space, it'd be hard to do, because people are like, hey, I love this. And it doesn't cost much, right? And then people are like, we don't think it costs much. And then people are like, and you can do it lots of places. Like, we're like, well, yeah, but we're not sure we can do it here. There needs to be a small reduction in the uncertainty in order to answer these questions more comprehensively. And the fact that they're straightforward to answer and probably pretty cheap to answer is good. But until that work's done, we're still going to be using scientific language instead of business language.
Well, we have dozens of questions in the chat here, in the Q&A, and I'm going to pick out some that I think are especially interesting. I invite my fellow speakers to do so as well. If you see something you'd especially like to address, why don't you call it out? There's one from Alan Lyserson, I hope we're pronouncing your name right, on policies. And Julio, I know that's a topic that you have thought a lot about. Alan asked, what would strong policy support be? Just as a reminder, our author team estimated that with strong policy support, it'd be possible to get 1 gigaton of carbon dioxide removal annually by 2035 and 10 gigatons by 2050. That's a lot. Julio, when you think about strong policy support in this area, what do you think of?
So before I answer that question, I want to actually speak to another question that came in that's related, that Kate Marvel asked, Dr. Marvel also at Columbia. She asked, how come there isn't more policy on this? Which is the precursor to the other question. Part of the reason why there's no strong, why we don't have the policy recognition today is that we have to remind ourselves that net zero is only like 2 years old. Most people just haven't even gotten that into their head that this is a thing we need to do. So most of the policy was about building clean energy. It was not about removing and reducing. And that shift is fairly young. Along those lines, there's a lot of science that we have on carbon mineralization, hundreds of years old in some cases, very strong and robust, but it hasn't been really applied to this problem in some cases. So We don't quite have the science aligned with the policy questions that we'd like in some cases, which is part of the reason we did this study. A third question, and this gets to sort of Peter's world these days, there aren't that many companies doing this. And so that means that not only is there not a lot of supply in the market that you can call up and say, hey, I need 100,000 tons. But there's also not a lot of advocacy because these companies barely exist. So policymakers just haven't been exposed. Another reason why we wrote this report. The good news is we've done some work and we've got a lot of stuff to consider. And in that context, I think we know what strong policy looks like. One of the things it looks like is please put some money into the science and innovation piece on this. There are so many things to learn on this. A little bit of money goes a long way. Second is we talked about spend a little more money on pilots. The pilots really will help, and we should have a coordinated network of pilots around the world. We should have pilots in Canada and China and Chile and other countries that begin with C, like California. We should have all of these things sort of rolling forward in a way that we can start to get a sense of how to make this work and also have a sense of the standards and the protocols that we would need. The last thing gets back to that standards and protocols piece. We need to start pulling these things away from a voluntary market sensibility and into a compliance market capability. So for example, this is not something you can get on the ETS because it's not a compliance option. This is not something you can purchase through the California Low Carbon Fuel Standards because it's not a compliance option. If we had a clean electricity standard that was a zero carbon standard, carbon mineralization would have to be an option. It is not an option under CORSIA, which is the aviation standard. It's not an option for the International Maritime Agency. So we have to start moving this stuff into a compliance market. That will help a great deal for scaling. One point of light on this, the United Kingdom is doing that. They announced a policy about a month ago in which they said by 2025, they would buy 5 million tons a year of CO2 removal, and they named direct air capture and carbon mineralization as two compliance options.
Peter, see your hands up.
Yeah, I just want to mention, so there is quite a lot of investor, Julio painted a little bit of a grim picture, and I don't disagree. It's not, these processes are not under very active commercialization right now. But there are other startups, which I'll be happy to share with people if they want to write to me, but also very large mining companies and indeed oil and gas companies are contacting us, everybody's shaking their head, about implementation of this in a kind of a vertical strategy where fairly large emitters might engage in capture and storage via carbon mineralization. So I'm not sure I'm at liberty to share the names of all those, but if people are interested in investing, you know, there's definitely a lot of opportunities out there.
I can concur with that. One of the problems is because we don't have a compliance market yet, there's not a lot of companies that want to feed into that market. And so there's this bit of a chicken and egg problem. My answer to that, chickens. Let's go out there and start making the science and the companies and creating the supply. Because once the supply comes online, there are already people willing to buy it, but you need to get that supply going first. That's part of the reason why you're seeing this interest in the investment is because people...
Chicken starts with C too.
Yes, also starts with C.
Okay, I'm just going to let that go. Holly Kaufman asked a very interesting, important question. And hi, Holly. Holly asked, what kinds of infrastructure might need to be built for any of these processes? And are there any water or air impacts? And could this lead to opposition from community groups or from the EJ community, environmental justice community? Any thoughts or comments on that?
Well, so it's really, there are so many things that under this umbrella of carbon mineralization that it's a little hard to answer that in aggregate. But some of the ideas about removal from air almost have no significant impact. Underground storage might affect groundwater compositions in ways we don't like, but natural waters in these regions are actually have below the EPA safe drinking water limits in dissolved metals. So that's a green light so far. water requirements for some of the storage, underground storage methods, including the ones in use in Iceland today, are large. And that's driving a kind of a movement to the seacoast.
Mhm. Let me echo that general sentiment. We're not talking about one things, we're talking about 10 things. And so when you say, what are the issues, they really need to be looked at differentially. There are some things that environmental justice communities might naturally like. For example, putting distributed basalt dust on farms and improving soil quality. There might be things that in that same thing they're worried about. They might be worried about dust content in the air from that process. They might be worried about leaching heavy metals or something like that. There's things to understand. That's part of the reason to have a science program. And ultimately, we would hope that environmental community, environmental justice communities would walk into these conversations with their concerns, but also with the recognition that I think all of this stuff is solvable. There's no obvious thing where you say this will take a lot of water, this will take a lot of land, this will take a lot of X. Like up front, it doesn't look like that's the case. But we would want to be a little cautious about what we commit to before we've actually done these pilots and done these direct assessments.
Stasha.
I just wanted to add that some of these strategies that we talked about today are already implemented at industrial scale. So those could be used as case studies. For instance, the use of mineral wastes from mining as fertilizers. That's something that's employed in Canada and the United States already. So looking at how those practices got up and why could be very informative.
One last point, there are some versions of carbon mineralization which could solve major environmental problems. One example of this is mineralizing fly ash. There's fly ash ponds all over the place. We could actually clean those up notionally. One of the better places to do this is actually in waste asbestos mines and asbestos heaps. And there could very well be a way to remediate that problem as well. I'm not suggesting anybody go out and start ripping up asbestos mines today. I think there'd be a lot of concern and caution about that. But in fact, it is real that some version of carbon mineralization could resolve existing environmental challenges.
That's a very interesting point, Julio. Maybe just worth elaborating on that. I mean, for example, what would the process of remediating fly ash using carbon mineralization look like? What would it end up with?
So Peter and Sasha are deeper experts on this than me, but some approaches look pretty easy. They could be like a tube and a fan. Some of them could be relatively benign. You start just trenching this stuff out and mixing it. Like with robots, it could be pretty benign. There'd be concerns, like civil engineering concerns you'd care about, but fundamentally, we're talking about pretty straightforward approaches. Peter and Sasha, please.
Well, one thing we haven't really dwelled on is remediation potential, so that in particular, ultramafic mine tailings often contain asbestos, and it's been a problem so that some areas that were mined in California are Superfund sites. The carbonation process will probably almost fully mitigate that hazard.
And then we would end up with piles of carbonated rocks that are no longer dangerous or present threats in the environment. Is that the idea?
That's right. And I think if I had thought a little harder about it, which I haven't yet, that might apply to a lot of so-called alkaline industrial waste as well. Not that they contain asbestos, but that they're gradually oozing nasty stuff into the water that would be locked up by carbon mineralization.
There's a nice connection there to cement as well. So pulling CO2 out of the air is what makes cement, one of the things that makes cement hard. So if you're destroying asbestos in a stockpile of mineral waste, you're also cementing the rock and turning it into something harder that has greater stability. So there's also potential to improve slope stability of these mineral wastes that are sometimes stored in enormous piles. And we all know that there have been any number of tragedies from mine tailing storage facilities failing in the past.
One quick shout out, if I may, because I know he's online. Dr. Rick Ryman of Rutgers is listening. He's also invented a set of technologies that bind CO2 in cement and mineral form. One of the things that he points out is that existing concrete actually has unreacted minerals. And in fact, one of the fastest and best ways to do this is actually tag existing concrete and reuse it and mineralize what's called the live concrete, the live part of that reaction process. So there's many things that can be done in this. And the deeper you get into this space, it becomes like an endless bonanza of ideas. Like there's so many cool things to do in this space. We really are at the edge of a whole new continent on this.
Yeah, you made the point, Julio, that this is not one process, but multiple processes, and we highlight that in the roadmap. We haven't really highlighted it here, but I think it's worth emphasizing that carbon mineralization provides the foundation for a wide range of different processes. We have some questions about cost, which we have not discussed yet. Philip Smith asks, any idea of cost per ton for CO2 removed? Would a carbon price of $50 to $100 make this economically viable?
So before my colleagues answer that, I want to point people to the National Academy's report that looked at this 3 years ago, and they gave a precise but unhelpful answer of $10 to $1,000. And in part, that's because they were covering so many different things. We're getting better at this now, and again, this is something Peter knows quite a bit about.
Yeah, so I'm responsible for the $10 to $1,000 partly. So let's give some specific examples. The process that's ongoing in Iceland for storage of CO2 in subsurface basalts. You can look at a paper by Gunnarsson et al. A couple of years ago in the International Journal of Greenhouse Gas Control. They estimate around $40 a ton. For the process they're currently doing, and I think it could be quite a bit cheaper. Also, turns out electricity costs in Iceland are twice what they are in the US. So take that number and multiply by 3/4 or a half. So on the other hand, removing CO2 from air is quite a bit more difficult than storing CO2 that's already been purified, obviously. And so the method that the Heirloom Carbon Technologies company is developing looks like it will cost between $75 and $150 per ton of CO2 net removed from air.
And in that exact point, some things like the concrete mineralization processes could be much cheaper. In some cases, just like working the mine tailings looks like it could also be a lot cheaper. Today, we're paying for robots to go out and stir the mine wastes and learn some data, but we again think that there's clear line of sight to stuff below $50 a ton when that stuff is fully up and running. Sasha, would you agree with that? I don't want to misrepresent the truth here.
I agree with those numbers. Those sound feasible. And we've got a price of $40 Canadian a ton. So of course you would have to multiply that by something less than 1 to get US dollars. But we've seen a bonanza in interest here and proliferation of startup companies just with that low price. And the government here in Canada is aiming to put the price up to $170 a ton by 2030. So there's a lot of potential even at $40 or $50 a ton.
In part because of this growth of interest and the apparent low target costs in the near future, the Department of Energy is including this in their carbon negative Earthshot. They have funds for carbon mineralization research. They've had that for many years, but it's growing and expanding. You're starting to see this topic now elevated within, say, the Clean Energy Ministerial and working groups under Mission Innovation focusing on the mineralization. In part, and I expect we're going to see bilateral partnerships, say, between the United States and South Africa, or between the United States and Canada. We're going to start to see these come forward with a specific topic of mineralization getting its own early attention.
Most technologies have some type of cost experience curve. With the more experience we get, the lower the cost. We barely started implementing approaches on carbon mineralization. Do you anticipate that as we do more, that costs will drop below the figures you're discussing?
Well, so let's take soil amendments. It's probably pretty cheap to grind up lava basalts and spread them over agricultural land. And so I think those numbers, even for CO2 removal from air, which is typically people aim for $100 a ton, could be quite a bit lower. But it is challenging from the perspective of so-called verification and monitoring, because you don't want to put a lot of basalt in one place. So you're going to distribute a little bit of basalt per square meter over a huge area. And now we have to measure, for the people who are paying, we have to measure the increased carbon uptake in small amounts per square meter over a huge area against a kind of a noisy biological background. So it's a challenge and a real research opportunity for those of you who are interested in such things.
We have an interesting comment, long one I want to read from Mylan Einstein, who says, we have developed a concurrent process similar to your crushed rock method, but totally underground. It's a two-phase process which takes advantage of both natural rock absorption and accelerated CO2 mineralization at low cost. During mineralization, the process is endothermic. We claim we can reach up to megaton levels with our process currently competing in the XPRIZE carbon removal initiative. Reversing the process is also possible by managing the thermodynamics. And then Mylan says that carbon mineralization at the surface is a contradiction to net zero because it's energy intensive, unless the utilized energy sources are completely renewable. Any thoughts or reactions to either the process, if any of you are familiar with it or have any reactions, or the assertion about carbon mineralization at the surface being a contradiction to net zero? Peter.
I'd have to know more about the subsurface process that's being described, and it's exothermic rather than endothermic. I don't know if that was a typo on Einstein's part or yours. With regard to the surface process, the net CO2 emissions from grinding up rock and distributing them on soil is the net. It's a net carbon uptake by a lot.
Yeah, I would agree with that too. It is clear that you can do ex-situ mineralization at the Earth's surface and in situ mineralization under the Earth's surface, and it's clear that you can do those each in a way that removes large volumes of CO2 from the air and ocean, or that captures large volumes of CO2 from the point source on net. The life cycle analysis is not very challenging, and there's lots of ways to keep it that way.
Mm-hmm. Well, please reach out to us, and we're happy to pursue the conversation. Peter, you mentioned in the course of your presentation a looping process. I think might be interesting to elaborate on that and talk more about what that is.
Okay, with the caveat that I am conflicted because I'm an advisor to a company, Heirloom Carbon Technologies, that is commercializing this, or trying to. It's really pretty simple. In fact, it's kind of embarrassingly simple. You take limestone, you heat it up, that produces calcium oxide and CO2. And so you store the CO2, you give the CO2 to someone who will store it or use it. And you use the calcium oxide exposed to the weather to take more carbon dioxide from the air. And that is turning out to be quite fast. Oftentimes we can get 75% carbonation in less than a week. So then you just use it over and over again. And unlike many of the methods that we've discussed, this way every atom of calcium brings many, many, many atoms of carbon out of the air before you're done with it. So it essentially drives the original mining costs to zero per ton of CO2 removed from air. And because it's so simple, I anticipate that it's quite robust, and that the cost estimates that are based on this technology will be correct, and they're not particularly speculative. So I'm pretty optimistic about this. And there are various variants of this kind of process that are under development by other groups that I'm perhaps less familiar with. But overall, it's almost as though we've overlooked this because it's so simple.
And the costs and the emissions associated with the heating process, Peter, those could be relatively low, you think?
Well, right. So we've done these calculations, the sort of net removal from air and the emissions associated with energy generation are small compared to the potential for CO2 removal from air. Heirloom Carbon Technologies is dedicated to not using fossil fuel at any point in their process. So they're thinking about electricity generated by renewable sources, or maybe even solar thermal heat sources.
While you've got the microphone, Peter, we have a comment that the risks associated to the Oman project is sea acidification by leaking residual CO2 from subsurface rock structures, particularly. Any comment on that?
Yeah, the dissolution of magnesium and calcium-rich rocks is actually more likely to act against ocean acidification and mitigate that problem. So that the for example, the natural process in Oman today that removes CO2 from air produces calcium hydroxide rich water. If that water were added to the ocean, it would mitigate ocean acidification and cause additional drawdown of CO2 from the water.
Yeah, the core chemistry is pretty easy, actually. CO2 is an acid, and these alkali rocks are alkali, they're basic. And so when you react them, you remove acids.
We have a question from the distinguished expert Adam Siminsky, who asked us to, hi Adam, he asked us to please repeat the point on water quality requirements. Maybe we talk about both water quantity and water quality and in these processes, and underscoring as we've mentioned that carbon mineralization is a lot of different processes, but for some of the key ones that we're talking about, would anybody want to elaborate on both water quality, water quantity requirements? Peter.
Well, let's just take CarbFix in Iceland as a starting point, since it's actually happening. The CarbFix phase 1 technology, which I won't go into, but anyway, had about a 20-to-1 water to CO2 ratio, maybe 25-to-1. So it's pretty water intensive. That's not something they worry about in Iceland. But so this is, as I mentioned before, this is sort of driving thinking towards the seacoast, where there's essentially unlimited amounts of water available. In terms of contamination, again, I don't think the Icelanders are too worried about this because it's tiny amounts of CO2 and a giant amount of water. But as I mentioned, in Oman, where you might expect to see enrichments of nickel or chromium oxides in the water, which would be quite dangerous, the actual measured concentrations of nickel and chromium in the waters coming out of these rocks are 100 times lower than the EPA safe drinking water limits. So we don't really know what will happen when we start monkeying with that, engineering that process, but right now it's not a problem.
I will add that in terms of water use, almost all of the time in these systems, you can use brine. So not a lot of fresh water. In some cases, you're waiting for rain to take care of stuff. You're putting stuff out on soils and the rain does the work, which has a tiny, tiny, tiny bit of dissolved CO2 in it. And in some cases, like with the cementation reactions, some of the CO2 mineralization pathways in the cement actually reduce net water consumption, because instead of using water to make the concrete, you're using CO2 to make the concrete. So there's actually, again, it really ends up being quite bespoke for each process, for each geography, for each mineral resource. And so there's no hard and fast rule. In a place like, hypothetically, the Kingdom of Saudi Arabia, where water costs are substantial and water access is an issue, there's still a way to think about the mineral resources of the kingdom and the water demands in a way which produces some good outcomes.
Yeah, Peter and then Sasha.
No, how about Sasha, then Peter?
All right, Sasha, then Peter.
Sure. I wanted to mention that this carbonation process often has the side benefit of immobilizing heavy metals. So those are often taken up by the carbonation products, or they end up being sequestered by just rust minerals that form as a result of the carbonation process. And this is something that, that has been documented in industrial reactor processes and also in passive weathering of industrial wastes. So we know that so long as the pH of the material stays high enough, all the heavy metals just get trapped by the carbonation products, which is beneficial.
Peter.
So as you can imagine, in the Arab world, where water is very valuable, people aren't necessarily inclined to take my word for it when I say that the water quality might not be diminished by these processes. So one thing that I've begun saying and should have said a long time ago is that pilot studies aren't going to have any significant negative impacts. Small pilot studies on the order of hundreds of tons or thousands of tons of CO2 per year are not going to negatively impact any significant number of people, but they will provide us with direct assessments of the effect on water quality and water quantity. So we really need to conduct those studies in order to assess these questions and be able to answer them with more confidence.
We have a number of questions on kind of R&D topics, and which we haven't talked that much about. We do have a chapter in our roadmap on this topic, but Raj Hardy asks, you mentioned a wealth of research has been published and recommend pilot projects. Is there any basic research in the lab critical to moving forward left to be done before moving to field-based scale-up?
We could go in parallel. There's lots of lab questions that are fun to ask, maybe more from a science point of view, but we could certainly design effective pilot experiments right now.
Yeah, there's no sort of gap that needs to be breached to start going. You can get going now, but that will, of course, reveal additional science questions as well. It's been my experience that people like technology and want to fund it and don't like science as much and don't fund it as much. But in point of fact, there's good science questions and good technology questions. Addressing both of them at the same time is a good pathway, and that would also address the policy questions in the shortest amount of time.
It would be interesting to just elaborate on some of the science questions. It's a core finding of our report that moving forward with field projects now is incredibly beneficial. In fact, we recommend it as it's a primary, principal step that needs to be taken. But what are the science questions or the types of science questions that you think could usefully be addressed? Anyone?
There's lots of issues about surface chemistry on the nano to micro scale, which might yield factors of 2 enhancement if we understood them. There's lots of questions on a larger scale about cracking versus clogging, whether as we form carbonate minerals in subsurface pore space, whether we'll clog everything up and cause the reactions to come to a screeching halt, or as in the natural system, whether those reactions will kind of make their own permeability and continue. That's something we can do in the lab, but really better in the field. Somebody take over from me. I'm sure there's many.
There's a good applied science question, which is something like, what's the role of microbes?
Yeah.
That's at least 20 careers. Like, people can dive into that one and learn a lot for a long time. That's true at the Earth's surface and in the subsurface. That doesn't even include genetic modification. It's just there's already microbes out there that do some stuff. There's kind of, again, I want to make sure that people are clear that there is not any missing science we would need to understand before doing the pilots. We can go straight to pilot now with a lot of stuff. But one example, in naturally occurring organisms like oysters or corals, I'm sorry, not oysters or corals. There's for diatoms, for siliceous organisms, they make their shells out of an enzyme, with an enzyme called silicase. Silicase is an enzyme that makes and breaks silicon bonds. Well, that sounds fun. There's maybe some way to use that. how does silicase work? How is it made? Is there an inorganic substitute for it? If we had it, how would we want to use it in an applied context? And that's more focused on sort of the applied end of it, but it's a terrific scientific question about how organisms make their shells. Similarly, I saw one of the questions came in and asked, is there some way we can accelerate the carbon mineralization process in existing organisms, something like oysters or corals? That's perhaps a more complicated question. Some of that could be done environmentally, some of that could be done genetically, some of that could be done through hybridization. You can go and go, but the answer is probably yes. There probably is a way to accelerate the way that living organisms take up calcium and carbon dioxide. And if so, there may be some way to do that that's beneficial and safe.
Love your passion for the science questions here, Julio, and it prompted hands from both Peter and Sasha. So, Peter.
Well, I mean, we haven't really dwelt on it today, but and it's a little bit of a third rail for some people, but there are many proposals to increase carbon dioxide uptake in the oceans, in the open ocean. And some of those, maybe most of those, would affect biological primary productivity. So for example, to pick the one that I think is most benign, adding calcium to seawater would probably increase CO2 uptake in seawater, would act against ocean acidification, but it would also make life easier for the calcifying organisms at the bottom of the ocean food chain. So that's just one example. Frankly, there's very few experiments on this, surprisingly few.
Even those few experiments, oyster farmers are doing a little bit of that now because the ocean has become so acidic that the oysters have a challenge. So they're beginning to make a Tums and just grind it up and put it in with the oyster farms just to keep the fry alive. And I don't think there's a lot of scientific monitoring around that. That'd be a good science program.
It would. We've started doing it in the lab, and we've discovered that we don't understand some things.
Sasha.
I want to add that there are a lot of biotechnological pathways that utilize microbes that have been studied to enhance carbon mineralization. And so the Earth is full of the goo of life. So it's always going to be part of any of these processes. And one interesting motivation for doing pilot studies and lab studies in parallel, what would be if you think about living ecosystems and microbial ecosystems that can accelerate these carbonation processes, you're going to get a different result if you do it in a petri dish or a glass house, or if you do it at a pilot scale outside. And so this is something that we've seen with microbes that are recruited from just blowing in the wind. You get different results. So you can study that at the fine scale in a petri dish or in a greenhouse at a university or a national lab, but you won't understand what's actually going to happen until you do it outside. So anything that's involving microbiology or living systems, I think we really need to go right to pilot and then figure out the details later, right as we go.
Well, shifting gears from the science to applications, Andrea Diacano asks whether there could be collaborations with diamond mining, since countries with ultramafic tailings seem to have high potential for CO2 sequestration. Any thoughts on that?
Could there be? There are. De Beers has already started doing this. And they've begun to explore how they can modify their mine operations to take up more CO2. Like the easy stuff is, instead of dumping it one way, dump it another way. But already that seems useful. It might be, well, if we're grinding up the rocks for the diamonds, maybe we can grind them a different way. But I'm pleased that the diamond companies are already thinking about this very seriously. And there's a pilot in Canada, there's a pilot in South Africa where people are trying this.
People include Sasha, so why don't we let her?
For sure. Thanks, Julio, for plugging that. The project is called De Beers Project Carbon Vault. And so that's involving Canada, South Africa, and Botswana as well. And so De Beers are looking at opportunities from the simple strategies that you mentioned, Julio, of just changing how tailings are managed, how they're spread out, for instance, to changing mineral processing circuits and utilizing different combinations of capture from air and storage of industrial emissions. So I know all of us were nodding earlier about having lots of phone calls from people in the minerals and energy industry. And these industries have made hard net zero commitments in the coming decades. So there's a huge opportunity and growing interest there, I would say. And did you want to add anything to that, Julio or Peter?
You're the expert.
The only other thing I would add is that it's not just limited to diamond mining. Many other kinds of mining extractions. We've talked about nickel mining, for example, but this is part of the reason why we're so enthusiastic about the pilots. There's actually places to start. We have a bunch of ground rock lying around.
And the infrastructure and expertise is already there, which we can leverage.
Well, let me pick up on that. So I don't think we're going to employ every single oil and gas reservoir specialist in the world. But when it comes to subsurface storage of CO2, and I'm extending beyond carbon mineralization to what people amusingly call conventional storage of CO2 underground, there's a huge need for the expertise that the oil and gas industry has developed in reservoir engineering as we start to inject fluids underground. I mean, I think everyone's aware of the potential for induced earthquakes, for example, and pressure management in these systems is super important. And there's just a lot of people in the world who understand this very well, who, not to put it too strongly, but some of whom may be in danger of losing their jobs.
It's a hugely important topic, obviously, is the job creation potential here, which we mentioned briefly. And then you've just picked up on, Peter. Kind of, any other thoughts on where there may be jobs and the number of jobs that might be available through expansion of this industry?
Process engineering, chemical engineering.
Also, geological assessments.
Yeah.
I mean, we keep coming back to this, but you know, right now, mining companies and exploration don't look for the good stuff for carbon mineralization. They look for the good stuff in terms of something like copper, which you can sell. If you can sell CO2 mineralization services, that's a new service. So there could potentially be a lot of geological assays done. There could actually be work to open mines just for this purpose. What Roger, our co-author on this paper, he calls quarrying, where you basically open a quarry to pull out rocks that react well. We haven't really begun to think in a comprehensive way about the potential abundance, but I'll tell you for nothing, if we get to a gigaton or if we get to 10 billion tons a year, that will be a lot of jobs. That'll be a lot of jobs for somebody.
Well, and we should keep in mind that no one's going to pay for this unless the carbon uptake is demonstrated. And so there's enormous number of jobs in terms of monitoring and verifying the different methods for removing CO2 from air and storing carbon dioxide.
You mentioned Roger Ains of Lawrence Livermore. I want to particularly call out his contributions to this roadmap, which have really been important, and thank him. He's played a really important role in the work on this topic. Number of questions on policy as we start, and Danny Broberg asked whether the 45Q tax credit in the US can support carbon mineralization. Julio, thoughts on that?
So I haven't gone into the latest amendments to know for sure. And of course, there's still stuff that's being negotiated between the House version and the Senate version of the amendments. But I've heard it from a DOE leadership that the answer is yes. They believe that 45Q, a straight reading of 45Q does include mineralization, and amendments can make that clearer. I'm not 100% convinced that's the case, but I'm prepared to accept it could be. And certainly if the IRS provided updated guidance to that effect, then the answer would be unquestionably yes.
Bob James says, would carbon pricing with rebates for carbon capture and sequestration be a good approach to support this? The Energy Innovation and Carbon Dividend Act includes that.
Yeah, that ends up being a very specific point of policy design. If you're talking about a fee and dividend structure, then everybody gets their fingers into it fast because they want the dividend to go to various things, whether that is equity or the treasury is a topic of much discussion. Nonetheless, directionally, sure. I personally think something like 45Q is more straightforward and transparent, but you could certainly do something similar with a fee and dividend structure. Let me also say that if the low carbon fuel standard in California just included carbon mineralization as a compliance pathway, you would suddenly see a lot of companies and projects jumping up. I think some of these fixes are pretty modest.
Yeah, I was going to mention the low carbon fuel standard. So I've been to Sacramento and talked to those folks a couple times, and I mean, an important thing about the California low carbon fuel standard, which is amazingly idealistic, is that in principle, they will pay for CO2 removal from air anywhere in the world because they know that the air is well mixed. And so CO2 removal in halfway around the world will benefit California. So it's amazing, but true. On the other hand, yeah, they haven't explicitly called out carbon mineralization as a method for removal from air or even storage. And they always says, you know, do some pilot experiments, show us once we understand how the monitoring works out, we'll add it.
Just kind of jumping around in some questions. We have so many, and I'm sorry we won't be able to get to all of them in the time remaining here. But Greg Jason has a very specific one on phosphogypsum. He says phosphogypsum via phosphate fertilizer manufacturing is a naturally occurring radioactive material that's historically limited what can be done with the material. And that's one reason we have these huge stacks in Central Florida. Does our study address this issue, and what any thoughts on that? Does anyone have any familiarity with that?
Enough to worry. I'm not a particularly, it's like that's not the first thing I would rush to do. In addition to the radioactivity, you might well immobilize uranium by oxidizing it, and CO2 is nothing if not oxidized. So maybe uranium would be rendered immobile, but I really would worry about what we're going to do with all the sulfur that we displace when we combine calcium with CO2 rather than sulfate.
But let me say that any day you can say phosphogypsum's a good day.
We'll have it.
But is this an example of the type of pilot projects that should be launched, you know, doing this on a pilot scale to see what the results are?
Yeah, and the Moroccans should lead the way.
Right. You can decide a priority order, like which one, like there's always limited budgets, right? You can decide what the seriatim is and in which order you should do A, B, or C. But at the end of the day, of course, you should do a pilot on this stuff, because then we'd learn something. Peter has credible concerns. Maybe they are really valid and we want to avoid that. Maybe there's a straightforward way to manage it, but we won't know until we do some work.
Well, that's a perfect lead into a, oh, go ahead, Sasha.
I had a quick add-on. I know someone who's grown a forest and a vegetable patch on a phosphogypsum stack here in Alberta. If you want to know more about it, shoot me an email and I'll put you in touch.
Oh.
Well, we're just about winding down. I want to kind of ask, I'll go to each of our speakers for kind of final thoughts briefly in a minute, but what you just said is Hula is a perfect lead into a question from Hula, Juho Leponen. Hope that
Juho Leponen.
Thank you, appreciate that. Who asks, where do you see the 1, 2, 3 first most obvious project opportunities for large-scale pilot project demo? Is there a lighthouse sector or project that we think should be undertaken first?
So first of all, glad you're here, Juho. Thanks for joining. This is like our favorite parlor game in the carbon mineralization community. Everybody has their own wish list. Like, what are the 5 places to go? Where would you go first? I'm going to start answering this question by not answering it and turn it to Peter, because he's doing pilots and Sasha's doing pilots too. So where are you guys most excited about? And then I'll add my list.
Well, okay. So, I mean, this is where my desire to, first of all, announce conflicts of interest and secondly, put my worst foot forward enters in. But so there are projects ongoing, as we've mentioned. 4401 in Oman, they are commercial. They need investors, but they also would welcome research money. And Heirloom Carbon Technologies, I also already mentioned, they are almost done with their seed round funding and moving into the next fund or the next step of investment. And I'm very optimistic about the outcome for them. But again, they need to be able to partner up with organizations that will store the CO2 and organizations that will supply thermal energy at a low cost and preferably in a CO2-free manner. So those are two big things. CarbFix is ongoing. Expansion of CarbFix globally, using that technology in basalt formations worldwide, particularly near coasts, is a huge opportunity. And it's really pretty easy to fire up pilot project. When I say pretty easy, I mean $10 million, but it's relatively straightforward to fire up pilot projects in that domain on a short-term basis. And there's a lot of industry interest in that. So again, government assistance in getting those things off the ground would be welcome. There's an activation energy barrier there that could be quickly overcome.
We are down to 3 minutes remaining. Sasha, any additional thoughts here?
Sure, I'll plug my favorites in the parlor game. I think mining and agriculture, they're two of our oldest, biggest industries with a lot of expertise, and they're already operating at scale in terms of infrastructure and supply chains. And there's an interest there. So we already have enhanced weathering for carbon mineralization occurring in agriculture. It's just we hadn't been thinking about it that way. It was just using rocks as a fertilizer because it helps get you bigger potatoes. So the monitoring, measurement, and verification is really the thing we need to tack onto that because it's already at scale. And then we can scale it up more once we know it's a good idea for carbon. With mining, the thing that I like the most is that there are projections that we need to increase the amount of critical metals that we're mining to bring everyone back up into the middle class, back to the middle class, and to, you know, make the green energy economy. And if we only need to have, you know, the mines we already have instead of twice the number of mines by using carbonation to make metal extraction more efficient, I think that's a good idea. And in the interest of time, I'll pass that back to you.
Well, let me just second something. I think the agricultural application really looks cheap and huge. And so those of you out there, the place where research funding is critically needed, and it hits a lot of sexy things like big data and statistics, but it's critically needed to develop these monitoring and verification methods for these very, very distributed applications of calcium and magnesium rich material. It's a wonderful opportunity. It won't happen without government research funding.
Let me throw a couple of other quick favorites on there. I like to go where the light's good. So I love the fact that Peter's doing this project in Oman, but you could do the same project in California. Let's do that, actually, up near Mount Shasta.
Yeah.
Yeah, but there's places to do this. If we've got all these asbestos mines all over the place, let's try one. Libby, Montana, wherever, there's places to go. We haven't talked about steel slag. Let's do that. Let's go to a place like Gary, Indiana, or Baotou Steel in China and start doing that. Or you know, there's places where we can go today and answer some of these questions. Get a range of processes, get a range of sites, get a range of mines, get a range of rock types, get a range of climates. 20 projects would sort the world. It wouldn't cost that much.
Julio took the words out of my mouth. Somebody asked for 1, 2, and 3 priorities, and we responded with 20.
Well, and we are at the end. We're out of time, and so let me just do some quick thank yous. First, I want to thank the entire great team at the Center on Global Energy Policy: Caitlin Norfleet, Natalie Volk, and others, Keo Lee, who helped put this together. Really appreciate all your tremendous work. Then I want to thank our co-authors who weren't with us today: Roger Ains, Colin McCormick, Ian Power, and Brianna Schmidt, all of whom played really central roles in this report. then thank our tremendous and incredibly expert speakers today, Peter Kellerman, Julio Friedman, Sasha Wilson. As I said at the beginning, the recording of this event will be posted on the website of the Center on Global Energy Policy. We will post the slides as well, so you can see the slides, and you can find the report on the website of the Innovation for Cool Earth Forum, www.icef-forum.org, or just Google this, and hopefully you'll find it. Our next event at the Center on Global Energy Policy is tomorrow on carbon capture in Wyoming, featuring, I am guessing, the distinguished Julio Friedman. And it is tomorrow at 1 p.m. Eastern time. So please join please join then. Thank you, everybody. Have a great day. All the best.
Thanks, David.
Thank you all.
Thank you all.